Welcome back to System Software. So we're right in the middle of learning about processes and how to actually implement them using the kernel system calls. Last time we went over process creation with fork and exec. So before I begin, questions on that? I know we went over a lot of, several system calls. There was a lot of example code last time. Questions from last time? Yeah.
I remember last time when we ran exactly, we started Bash too, right?
No, Bash is a separate program. Bash is the parent process of the program that you run because you run it from Bash. Okay, I have this in some board. So yeah, Bash is the process that invokes your program. So if your program is called find, we had a program called like forkexec.c last time. Bash invokes it, but when we do exec, it replaces this process's run a program. But Bash is not affected. Bash is the parent of the process we're running. We're not affecting Bash in any way. It's still running in the background. Did I make that answer your question? All right, other questions on process creation? Okay, let's go over the homework. So I asked this last time, what's a process? It's a running program. Hopefully you know that by now. Which system call creates a new process? Fork, yeah. Not exec. Exec doesn't create the process. Exec just, what does exec do? Yeah, and how does it do it? It just replaces the memory segments of the current process. Like a virus, it replaces what it does, but it doesn't make a new process, doesn't make a new cell. Okay, so when a new process is created with fork, are all open files or just standard I/O open files duplicated when the parent process is created? All files, yeah. All files are duplicated. Yeah.
Are they duplicated or is the file descriptor just duplicated?
The file descriptor, well, the file descriptor is duplicated. Well, okay, so this diagram illustrates it probably the best. The file, remember, the open file is not the same as the file. You can think of the open file as a pointer to the file. So many processes can open the same file. So they can read from the same file or write to the same file. So the kernel maintains a table of open files across all processes, and then the process has a table that points to those open files in the kernel. So when we have a fork, like we have here, then the child duplicates the parent's table of open files. And so those pointers just still point to the same open files in the kernel table. And then in the kernel table, those are pointing to the actual files, like the inode. All right, other questions? Is that clear? Other questions on this? So all open files are duplicated when you call fork. Pretty much everything is duplicated when you call fork. What's the only difference in the new process? The return value. The return value of fork is the only difference. That's how we can execute different code within the same program after calling fork. So this was question 4. So when a new process is created, how can a program determine whether it's the parent or the child process? So it's the return value of fork, and what are those return values? How do they differ?
0 for the child and non-zero.
Yeah, 0 for the child and positive, non-zero positive number, the process ID of the child for the parent. And then error is -1, as with many syscalls. Okay, what system call can we use to change what program a process is running? Exec. Yeah, that's the syscall that changes what program it's running. So remember, we have this 2-stage process for creating a new running program, a new process that has a different running program. Fork duplicates the process. It's like cloning the process. And then exec, if you want, you don't have to use exec, but exec will replace the current process with a new different running program. Okay, so for number 5, that was exec. So what does this return if the system call is successful? If exec successfully runs, what does it return? It doesn't return, yeah. It doesn't return because now a new program is running. You called it in the original processes program. So when you replace all of the memory segments, including the code of that process, there's nothing to return to anymore. That code is no longer there in the process to run. So instead, you can think of exec as a call to main of the new program. All right, questions on this? Questions on the homework? Any questions on the project, which is, okay, we have one more week for the FS project. Questions on FS? Yeah.
So, when we're on the FS project, whenever we're reading in the file and then we write to the other file, is there like a certain amount we should read in? Because I wasn't sure. I just did like 16 bytes arbitrarily, but.
Oh, you should read all of it, the whole file.
Oh, I was doing it so like
I see.
16 bytes at a time and then write 16 bytes.
Yeah, that's fine. That's fine.
Okay.
I'm sure there's probably some optimal, amount to do, but it's just a trade-off between how many calls you have to make for how large the buffer is. The system calls tend to be like slow, and you have lots of memory, so you can probably do gigantic. Now the system may not give you all that data at once, but you can have a very large buffer to try to do this more quickly.
Okay. Cool.
Yeah, but it doesn't matter. You could do 1 byte at a time,
Yeah.
and it would be equivalent.
I was originally going to do that, but then I realized like, wow, these are probably really slow. I shouldn't be
Yeah.
doing that.
That's right, yeah. If you have like a 10 meg file and you're doing 1 byte at a time, that's a meg of sys calls. And
It's probably also pretty slow, but.
yeah, but it doesn't matter. I mean, the test cases, as you saw, are really small files. We're not going for like, system level performance here.
I wonder how the actual copy command does it.
You can see it. I dug into it just to like see the. I have notes on it somewhere, but yeah, let me know on that stem, and I'll point you to where the actual code is. It's in the copy command, in the CP command, and you can actually see the code. It's pretty complicated. They have like basically a separate library for copying, and they have some efficient versions of it. I think also if the file is like sparse, if there's little data in it, it'll only copy the parts that are non-zero or something like that. It has some very efficient code. But yeah, ask me on that stem, and I'll point you to the actual code. It's in like, if you want to search for yourself, it's in this project, GNU Core Utils, or at least that's the one we have on our system. So if you get the source code for this, which is, I wonder if there's a web version of this. I can't remember. Well, I have it. You can see inside the Core Utils project, there's a cp.c. So this is the actual copy command that you're using on the command line, and there's like a separate library for doing the actual, this is the do copy function. Do copy. And in here, it's calling out to a different copy. So it's doing a lot more stuff than our copy command. So there's the copy call, but that's another, one of their own library calls, which is defined here in copy.h. So you can see there's a whole bunch of it's not trivial. They have a lot of take a look at it. Here's copy.c. So this is the file that does it. Copy.c. So here's sparse copy, and you can read how they do it. I don't know the algorithm. I didn't look that closely in it, but yeah, you can actually see how they do it efficiently. And all this stuff is open source developed. You could even ask on the developer list. I'm sure someone will, say I'm a student, I'm interested in your algorithm. I'm sure someone will get back to you and explain stuff, or maybe not. So here's a function for writing zeros, I guess, more quickly. But yeah, there's the actual code for the copy function. And so the copy command has tons of options. So all these options are being supported here. So you can make it not overwrite. You can make it copy recursively a whole subtree. So they have all these features in there that are also in the code. So our copy command is like 50 lines, but theirs is hundreds.
I can make an easy
Oh yeah, right. You just call the system's yeah, but that's calling this program.
Yeah, but it's technically one line.
True. Yeah. True. But it assumes it was already implemented by someone, right? Not with syscalls. All right. Other questions on FS? Okay, we did homework. We did questions. Let's do attendance. All right, before I go into the next lecture, I just want to review quickly the process stuff we went over. So the homework reviewed it, but I want to just show the code one more time, the kind of complete fork and exec code. Okay, so this program, first thing it does, it calls fork. What does fork do? Duplicates the process, so now we have two processes that are running this program. When fork returns, they're both at this point in the program. They're at the point in the program right after calling fork. The child returns 0 for fork returns 0 for the child, and it returns non-zero and non-negative 1 for the parent. So inside the child, this code's going to run, and inside the parent, this code's going to run. Questions on that? Questions on that semantics of fork? Yeah. Okay, so when this program starts running, it's a single running process called, fork exec sleep is the name of the program. We call fork, and then in that call, the control is transferred to the kernel. The kernel duplicates the process like so. So we call fork, and now there are two processes. You can see memory of the parent is copied to the child, and all the open file descriptor tables are copied, as shown here. And so at this point, we've got, after fork returns, if it's successful, after fork returns, we have two processes. They're both running this program, and they're both at this point in the program, right after the return from fork. Is that clear? And then for the child process, the return value of this function is 0. For the parent process, it's the process ID. And so both programs will then assign that value to PID, their respective values, 0 for one, and then the child processes PID for the other. And because those two values are different, this switch statement will then go to case 0 for the child, because the value of this expression is 0 for the child. And it'll go to this case and execute this code. And the parent process, which is now a separate process with its own memory, its own code segment, will branch to or jump to this code and start executing this code. Is that clear? So it's the same program, but it's being run in parallel twice in two different processes. Because of the return value of fork, one is running this branch, this block of code, and the other is running this block of code. So it's the same program right now. So program A, you can think of that as fork exec sleep. We call fork, and both processes are running the same program. It's the same program being run at the same time. As if you had opened two instances of your browser, same exact code, but running twice in parallel. Or imagine running on two different machines. You have the same program running on two different machines, same idea. Okay, so now that we have two processes, they're running the same program, we use exec to replace the processes, in this case, the child processes, running program, what program it's running, with a new program, and that's the exec syscall. So remember, the exec syscall doesn't create a process, it just replaces the memory of the currently running process. So this version of exec takes the path to the program, and then argv, which is where this argc and argv comes from. That's where the parameters to argv come from. They come from exec. Eventually, it will go to the the call to main. You could think of this like a call, indirectly a call to this program's main function, which is how why you write C programs with a main function. It's a function. Someone has to call it. You can think of conceptually exec as calling that main function and passing in this argv as the parameter to main. And then the environment, that's like path, and that's other stuff. We didn't talk too much about that. Read the Linux programming interface for more about that, but it's just a kind of universal set of key value pairs. Okay, and then when we call exec, what does exec return if it's successful? It doesn't return. So as long as exec is successful, then this code won't even run. Instead, we've basically jumped to the main of our new program. In this case, we're running the program called sleep. We're jumping to that main function, and this code from this fork exec program is no longer in the memory space of the new process we created. Questions on that? Yeah.
Do you really have to put break after exit?
No, but it's good practice, I guess. No, you don't.
It makes it look neater, I guess.
Yeah, it's a good idea to be in a good habit of using break, because doing something like this is it'll fall through if you use case statements, so it's good practice to do it. Some compilers will even check. They should sort of know exit. You could also redefine exit. Exit is not necessarily the exit function. So exit, if you defined your own version of it, it may not actually. Yeah.
I was going to ask, is there any difference between calling exit and returning from the main function?
That's a good question. I think I don't remember the specification, but I think when you do return, when you do return, I think the same stuff that exit does happens. It does like cleanup of the memory and closes the process. I think the same thing happens. Okay. I'm pretty sure, but check the Linux programming interface book. If you look at the index, look for exit, it'll describe it. And also a minor thing which I learned for doing this class is there's this underscore exit. This is the actual syscall version. This is the library version. This will exit immediately without doing cleanup, and it's recommended to do this for. Yeah, I can't remember. It's in the book as well, the Linux programming interface book. But I don't remember the difference. But I'll say it in the manual, since I can't keep all this in my head. But this underscore exit, this is the syscall, and it doesn't do any of the cleanup of the C library stuff. So, for instance, if you have a printf statement and you tried to write some data and you call underscore exit, you may lose that data. It may be in a buffer somewhere, and when you call exit, standard out closes. And that data that never gets flushed to the buffer. So yeah, you can say it terminates immediately. Anything's closed immediately. So if you have data that you haven't written out with the syscall, you've only used the C library call to write or print, then you may lose that. But the section 3, the C library version of exit, does so-called normal process termination. So it flushes buffers, flushes standard I/O streams. And you can read this for all the stuff that it does. And there are even special handlers you can insert into programs for they're like events that happen on calling main and calling exit. But super fine distinctions to the system stuff. We don't need to know it for this class. Check the Linux programming interface book for the details on that. But this is the pattern that the LPI book uses. They say don't bother calling exit on the child and in the parent. But yeah, good detailed question. All right, other questions on what's happening here in this code? So just to kind of reiterate this diagram. Oops, let's do it this way. We've got our program here we call fork. Now we've got these arrows indicate that we've got 2 running processes. So this is one running process, another running process. In the parent, I didn't even bother calling wait, but in the parent we could call wait so that it would stay alive until the child exits. And in the child we call exec VE on program B. In this case it's sleep. And now that program is running. Questions? Questions on this? Okay, so let's see this program in action. So I've put some. Oh yeah, so the child process I'm calling is now called sleep. I did that so we can actually see the child process change its name. So I'm going to sleep at the beginning here before we call fork. So that way we'll see. So I'm basically inserting a timeout like here and here and here. So we'll be able to see at each point in this diagram using the process command, the process table. We'll be able to see these processes being created. Okay, so I built it. Let's run it, and I'll immediately pause. I'll stop it, and we can see that there's a single process running. That's the process that Bash created for me. Questions on that? So I'm here in the program. I'm sleeping here in the program. Probably could have used like a debugger to show this better, but I just, quick and dirty sleep command. So we're right here in the program. We're sleeping for 10 seconds, and actually let me sleep here as well. So we're right here in the program. We have a single process. Okay, so now you can see we're here. It called child PID, which was what the parent ran, and it ran inside child process. So we have two copies of this running program. One of them is here, and another one is here. Two copies of the running program. And they're both the fork exec sleep program that I ran. They're both still that same program, they're just running twice. Questions on that? Okay. So now you can see the sleep process is running. Let me run this again. Let me have this one wait a little longer. Actually, I could have it wait for the process. It's probably better, but. So wait 10 seconds here, and then we'll so now we're inside the child process. So at some point it will start running the sleep program. And there we go. So when we were at these 2 points in the programs, we were in the fork exec sleep program, 2 copies of it. After this sleep, we started, we called exec on the sleep program. And you can see here that at that point, the process table used the new name of the program. So this, you can see that through this sequence of commands here, this is process ending in 24. It still exists here. Oh wait, no, that's the old process. So this process here is process ending in 71. It still exists here. And it still exists here. It's still running. And the child process had this process ID ending in 17. It's still running here. And you can see that this has the same process ID because it's the same process, but exec has replaced which program is running. And so the process table has the name of that new program. Questions on this? So this diagram, it's listed in the notes. It's figure 24.1 in the book. This shows you diagrammatically what's going on here with each of these calls. Questions on this? Okay. All right, so that's fork and exec to create new processes and change the running program of a process. Let's now take a look at how we can play with the I/O of running processes. Okay. So So remember when in Bash we had this feature where if we run a program, normally when we run a program, say I run cat, what does cat do? What's the cat program do? Yeah, it reads from standard in and just writes it to standard out. I think a program you could all write right now. So if I write something into standard in, where's standard in coming from right now? Bash. Well, Bash, whatever Bash had, and Bash had my terminal, my SSH terminal. That input is going to Bash, and that's now what cat has. Cat has the terminal as the input and the output. So I've typed here in my terminal, that went to the standard in of the cat program. And you can see that the cat program takes the standard in and writes it to standard out, which is also my terminal. Questions on that? And in Bash, we could tell Bash to, instead of just copying whatever the standard out Bash had, to instead use a file as standard out. So I could make, and you can even create new files this way, and create new text files this way right on the command line without even using an editor. So when I run this command, where's standard in going to come from? Whatever Bash gave it. So it's not from Bash, it's from the terminal that Bash was invoked with. The Bash was invoked with SSH, so SSH gave it the standard in from the terminal. And where's the standard out going? To this new file, my new file. So when we run this, and I put things into standard in, it should go to my new file.txt. And indeed, when I close this file, so Control-D can close the file, I'll now have this new file in my directory called my new file. And I can, let's use Emacs to do it, I can view this file with Emacs, and you'll see that it has the contents that I gave via standard in to cat. Questions on this? Questions on this redirection? Yeah. Yeah, it'll just wait. It'll just wait indefinitely for input. Yeah, you could kill that cat with Control-C as well, which will also close standard in. Okay, questions on redirection in Bash? And so why is this possible? So why is it possible that cat, the same program, can write out to different files? So I could change this file name. I could have any file name here. I could even pipe it, right? I could pipe it to another command. Why is it possible for cat, without rewriting the program, how come cat can go to different outputs? So presumably cat just says printf. Why is it possible for cat to go, yeah? Yeah, that's right. So the process, these programs are written to use standard I/O. And so every process is given 3 open files, standard in, standard out, standard error. And because the program is written to use standard in and standard out, whatever process creates the cat process, in this case Bash, when Bash creates it, Bash can decide what I/O it has. And so this is one of the great features of Unix. One of the innovations of Unix was to abstract away I/O decisions from programming. So you don't have to, as a programmer, decide what output device or input device you're going to use. You can instead just use the standard, and then your shell program or whatever is using that utility, that will decide what your I/O is going to be. Make sense? Yeah.
So if you just use cat with no arguments and pipe that into another program, isn't that entirely pointless?
Yeah, kind of. Yeah, because you could have just used. So I mean that's so cat is it's like the identity function in math. It just takes standard in to standard out. Yeah, it's more useful when you redirect it. I mean that's sort of the point of it, is that it allows you to redirect stuff. Yeah, but yeah.
It's like attaching a hose to another hose. Great. Now you've got a longer hose.
Yeah, I mean, in this case, longer is probably not more useful. It's probably slower. But yeah, I think its purpose is for doing redirection, reading in files, managing files. But in the Unix world, it's all about having good defaults or some default.
Right.
And so, what default do you have?
Yeah, I wasn't saying it was a bad thing.
But yeah.
It's an observation.
Yeah, it is. It's the identity function. It's the function that takes one value and just returns that value. You can think of it like that. Actually, I think the program is called cat because it's concatenate. So its original purpose was like, you give it multiple files to concatenate. And I think the users, the developers are probably like, well, we need a good default here. We can't just, die when somebody runs cat, so let's just make it standard in, because that's the Unix philosophy. So it kind of illustrates it, kind of illustrates the philosophy. All right, other questions on redirection in Bash? Okay, so we went over the role of standard IMX in this. So how can Bash implement this? So remember file I/O. We went over 3 syscalls: open, to open a file, and then you get, you open a file. Read and write will read and write bytes to and from that open file. So the question is, just as a little review, for read and write, how do you reference the open file? The file descriptor, right. And where does the file descriptor come from? What syscall gives you the file descriptor? Open, yeah. So open returns a file descriptor, and remember this file descriptor is an index into a table that just keeps track of which open files you have. This is not the file itself. Remember, the file is, you can think of the file as the inode number. This is really a pointer indirectly to the inode number. So you can have multiple open files, multiple file descriptors for the same file, because it's like a pointer to that file. It's returned by open, and it's used by read and write. Okay, this is just to get started, I want to show an example of just using write to the standard out file descriptor. Oops. Okay, here is a hopefully pretty straightforward program that just writes to the standard file number, or standard file descriptor, standard out file descriptor. So normally when you use like printf, you use the stdout standard out file, but that's a C library file. That's not a file descriptor. So this is like the distinction between fread and read. So the file descriptors are actually, let's see, I have this in the slides. Ooh, I thought I had it in the slides. Okay, well it's in Unistandard, so I'll just go there. So the standard I/O file descriptors are, by convention, the first 3 file descriptors in the table, 0, 1, and 2. So this is C base 0 tables. And 0, by convention, 0 is standard in, 1 is standard out, and 2 is standard error. So file descriptors are just a number. They're just an integer. They're an index into a table. And the Unix standard I/O convention is that the first 3 entries into that table are the standard I/O files in this order: standard in, standard out, standard error. And so the Unix standard library just gives you macros, so you don't have to use numbers, but you could just use 0, 1, and 2 as well. So what this program does is it just writes this string to the standard out file descriptor. Questions on what this program does?
So is it writing it to the file of the file descriptor, or is it writing it basically adding it to the descriptor of it?
So this is just like if this is just like when we had file. This is the same thing as when we had open. So remember, this is from our class on syscalls. So when you call open, you get a file descriptor, and that's what you use whenever you want to write to that open file, right? Use that file descriptor. But for standard I/O is already given to the process when it's created. So those you can think of those as already being opened for you. So you don't have to call open on them. They're just already there available to you in the process. So that's why we don't need to call open on standard out. It's already opened for you. And so you don't have to call open. You can just start calling write, and you can just start immediately writing out to standard out. And this is how you do it. You write to, file descriptor 1, but for avoiding magic numbers, you can use this macro instead. Does that answer your question? Yeah. Other questions on this? So these you can think of these as already opened files for you. So when cat runs, when bash runs, the programmer can always assume that these 3 files are already open and ready to read and write to. That's how the standard I/O works. They're already ready to read and write to. The programmer does not have to do any decisions about how to open these or where to write to or where to read from. They're already open files. So that's why we can write this program here where I could have simplified this by just having a single write and just putting the text here. Okay. So here's our program that writes to standard out. So what should happen when I run this program? What do you expect to see? Hello world, right? I should see hello world, and where I should see it, right? Why should I see it in the terminal? Because it's writing to standard out, and what is standard out when I run this program? The terminal, because that's how bash invoked it. So bash invokes this process. It inherits whatever standard out for bash was, and that's the terminal. So when I run this, I should get hello world. So the program the program's not very amazing. It's a hello world program. But what it's illustrating is that without opening any files, I can just immediately start writing standard out because it's already been created. Okay, questions on this? Yeah.
Do you use SIT just for the parameter kind of?
It's just the type of the parameter. It's like a special type for the number. I don't remember. This is just This is just what. S type. Yeah, I don't know why. It probably should be S size T. They're all like a different kind of integer under the hood, different kind of integer, and I don't remember which is which. But it should be size T, not S size T. Sorry about that. Yeah. But anyway, these are just like special types that reflect the limits of the machine. But yeah, don't worry about those. Just follow the manual for those, as I failed to do. Yeah. All right, other questions on this? So this is you can just immediately start writing to the standard out file. And this under the hood is what printf does. Printf is writing to the standard out C library file, and backing that C library file is this file descriptor 1. Okay, so that's just writing to standard out. Here's how we can start doing some redirection. So we can oops. Uh-oh, I got a low battery. Give me one sec. Okay, sorry for the delay. Okay, so that's writing standard out. So here's how redirection works. Redirection works by using this syscall called dupe. Dupe will duplicate a file descriptor. And remember, the file descriptor isn't the file, it's just a pointer to the open file. Or it's just a description, it's an index into the table of open files. So if we duplicate it, we can write to the same file using two different file descriptors. So here's code that will duplicate the standard IO file descriptor and give us a new number for that file descriptor. So it's the same code at the beginning. We just write this hello world to the standard out file descriptor. And then we duplicate the file descriptor. We get a new file descriptor for this open file. So this is not going to be 1 anymore. This is going to be a new file descriptor, whatever the next file descriptor that's available. In this case, it'll be 3 because there's only 3 open files. So the next one will be index 3. So now we have 2 file descriptors, 1 and whatever dupe FD is, that we can write to the same file. So here I just write a different string, goodbye, to that dupe FD file descriptor. Questions on this so far? So this dupe command just creates a new file descriptor that points to the same open file. And I think I've got, where's my... Okay. So let's run this program and let's see what happens. All right, what should I see, or what should happen? What should get written? Where should it get written when I run this program? So this beginning is the same, so I should expect to see hello world. What should I expect to see or not see with the second write? Where will the second write go to? The same place as standard out. So it's a different file descriptor, so it's not technically standard out. Standard out is file descriptor 1, but it's the same open file. It's pointing to the same open file. Whatever that was, the programmer doesn't know. We don't care what it was. Bash set it up for us. But now we have 2 file descriptors for the same open file. And what was the open file here for standard out? The terminal, right? The terminal is the open file, because remember, files are not just storage on disk, they're an I/O abstraction. So what should we see when I run this program? Hello world and goodbye, right? So I put a sleep in here, and we see hello world and goodbye. Are you amazed that you see? Not very amazing, right? Not very interesting. So we're just duplicating the file descriptor and then writing to that copied file descriptor. And so it does exactly what we expect it to do. Not super interesting, right? So it's just, what's the point? Why have 2 file descriptors to write to the same file? Okay, questions on the behavior of this code? Yeah? Yeah, you could do that too. But here in this case, we didn't open the file in the first place. So there's no way to call open again for standard I/O. And that's kind of the rub, right? Is if you want to, play with this, but you don't want to be responsible for opening the file, then what do? Okay, questions on this code, this duplication? Okay, so here's a slight variation of this, is kind of what you described. In this case, we're opening a file. Well, all right, let me give some context for this. So why would we bother using dupe? What's the point of doing this? What's the point of this lecture? This lecture, we're talking about redirection. So the goal here is to take standard out and redirect where it goes. So redirection is one use of this. So recall when we used cat here on the command line and I wrote to some new file, what the cat program, what bash did is it changed where standard out was going. It changed it to a file instead. So actually, I'm gonna skip one of these examples to move this along. So remember what it did. It changed where standard out was going. So to do this, there's a variant of the duplicate syscall, which will replace a specific file descriptor for us. So what dup2 does is it says, take an existing file descriptor and overwrite another existing file descriptor. So if we can overwrite an existing file descriptor, how could we use this to say, change standard out to go to a file? How might we use dup to do that? Yeah. Well, yeah, you could overwrite standard out with, well, if you overwrite standard out with standard in, they'll both be, it'll be the terminal, right? So it's close. We're going to overwrite standard out. Yeah.
The file descriptor of the new file, and then use dup to.
Yeah, that's right. So you can replace standard out. So this is what this is going to look like here. We can open a new file, take that file descriptor, and replace standard out with that file descriptor. Whatever standard out was, we can replace it with the open file instead. So that's what duplicate does for us. It allows us to do redirection, among other things, allows us to do redirection because we can now play with what the open file descriptors are actually pointing to, what files are actually backing them. So for cat and all these programs, they're expecting file descriptor 1 to be standard out, and it doesn't care what actually open file is actually there at file descriptor 1. And so what bash can do, or any file that's creating processes, we can make a new file, open a different file, and replace standard out with that new file. Yeah.
So does the file descriptor number stay the same if you change the files?
Exactly. Yeah. So that's what dup2 does. So what happens under the hood? You could use dup for this as well, but what happens under the hood is that this file is closed, and then dup takes an existing file descriptor and replaces the next lowest file. So it's kind of a complicated semantics. It creates the next lowest file descriptor for you, but the one you just closed is the next lowest one. So what dup2 does directly is it just says, all right, I'm going to take whatever this open file is, and I'm just going to make standard out now be this open file. So if this is file descriptor 10, now there's going to be a different file descriptor for 1. I mean, it's going to be the same file descriptor 1, but it's going to be a different open file. It's going to be the same open file as FD. Maybe that was more confusing, the way I described it. So here's an illustration. Here's file descriptor 1. This is the standard out. And you can see that file descriptor 20 is pointing to the same open file. So if originally standard out was pointing to, say, the terminal, I could open a new file that might have file descriptor 20, and then use dup2 to overwrite or replace where FD1 points to. So after calling dup, FD1 will now point to the same open file that FD20, file descriptor 20, is pointing to. Does that kind of make more sense? Let me show this diagrammatically as well. So here's what this code does. So bash, let's do it this way. So bash is running, and actually, well, we don't even, yeah, let's start with bash. Bash is running. Its input and output is to the terminal, and when it forks this new program, redirect standard out, what happened? What's the standard out? If you create a new process with nothing else, what standard out or what file descriptors does the forked process have? Same as the parent process, right? So when we first create our redirect standard out program, it has the same I/O as the parent process. And then when we call open, it now also has this redirect standard out dot out file that it also can write to. So this is the open. This is what the open command does. And then when I call dup2 for standard out, so this is file descriptor 0. This is standard in. This is file descriptor 1. This is standard out. So when I call dup2 to take this open file descriptor here, so let's say this has file descriptor 3, then I'm saying take file descriptor 3 and make file descriptor 1 point to that file. So now I've redirected 1 to point to the same file as file descriptor 3. So this is what dup2 on file descriptor 1, file descriptor 3 overriding file descriptor 1, that's what this does. Questions on that? So it's like plumbing. It's just taking this existing pipe to standard out and redirecting it or overwriting it so now it points to this file. Questions on that? I can't tell if this is very simple or you're just completely confused.
Is it going to
yeah.
write it like to the file, like specifically, or is it going to write it to the output of the file, like whenever you go to like duplicate? I think that's what is like confusing. I was like trying to understand if it's touching the output or the actual like code inside the file.
It's just, think of it as changing the pointer. So if you think of standard out as a pointer to a file, in this case, when it's originally created, the file is the terminal. Because remember, files are not just storage on disk. They're outputs or inputs. So the terminal is our SSH session. And when Bash creates it, its output, its standard out, is to the terminal. What dup2 does when we do dup2 to replace standard out is it overwrites what standard out is. It overwrites what file descriptor 1 is. So no longer is it the terminal, now it's pointing to this open file. So let me show this as a table, which is what the Linux programming interface does as well. So if we have our file descriptor table here, we've got 0, 1, 2, 3. And say this is our terminal file. So this is what, if you read and write to this file, it goes to and from our terminal program. And file descriptor 0 and file descriptor 1 and 3, or 2 rather, they're all reading and writing to and from the terminal. So when I call open my path, I now have, think of it as a pointer to my open file here. Let me give the actual name. I'll call it redirect standard out.out. Think of it as if it's pointing to that file. But this file descriptor 3 is not the file itself. Think of it as a pointer to the file. So this is what open does. This is what open does. And then what dup2 does is let's use a different color. So what dup2 does is it takes 1 and replaces it with whatever file descriptor 3 was pointing at. So you can almost think of it as like copying this data here. It's like copying whatever was in the file descriptor table for 3, copying it to entry 1. So now, if this is like a pointer, then whatever 3 was pointing to, 1 now also points to. So this is what dup2 file descriptor 3, file descriptor 1 does. Does that kind of help? Let me draw this again with a brighter color. So now this is being redirected here. And that's what dupe 2, that's what dupe 2 does. It just takes this open file entry and duplicates it here in entry 1. So these files aren't being affected in any way. It's just, think of them as the pointers to the files. So when you invoke the process, file descriptor 1 is pointing to whatever the parent process gave it. So by default, it just copies whatever bash had. And so that's the terminal. But if we don't want 1 to point to the terminal anymore, we can open a new file and then use dupe 2 to change where 1 points to, which file descriptor 1 points to. Is that clear? Is that clear? Questions on this? Questions on this? Yeah.
Are file descriptors just virtual addresses?
They're not addresses. They're just, it's like I don't know what the exact format is, but it's a table of information. I mean, it points into a kernel the kernel manages it, so it's kernel dependent. So the kernel just has a struct that keeps track of the path of the open file, where you are in that file, and the process table. For each process, it keeps a table of those open files that points into the kernel's open files. So they're not even like virtual memory addresses. It's literally just sort of metadata about the open file, like where in the file, what position you're in, what file it is, what inode number it has, if it's backed by a storage. I don't know if that helps. But no, it's not a virtual address. There's literally just like a table, like an array of structs that's indexed, that you index into, that the kernel adds and removes from when you call open or dupe. Other questions on this redirection? Yeah.
Just on understanding well, so one is the file descriptor recipe out, right? So by redirecting it to point to this thing in that file descriptor 3 is looking at, the
Yeah.
recipe out isn't going to use the terminal anymore, but to whatever that.
Exactly. That's the key point. So when we first write to standard out, it's going to the terminal because that's what bash gave us. When we open a new file and replace what standard out is pointing to, here we're still writing to standard out. But where is it going to go? It's going to go to that file we created, not to the terminal anymore. That's the punchline of this. All right, so let's actually run this code. Okay, so when I run this program, what should I see being printed out? So we have this write to standard out. Originally, it's the terminal. What should I see being printed out?
The first write will go to the terminal itself, and the second write will go to the file.
Right, the first write will go to the terminal, so we should see this being printed out. But when I do the second write, we shouldn't see that. We shouldn't see that being printed out, right? What about printf? Where should we see that? Will that go to the terminal? Or will that, what? It'll go to the terminal. Okay, let's take a look. So we only see the write to original out happening here. We don't see this write written to this redirect standard out, and we don't see this printf. Where did the printf go? To the file. Why? Because printf writes to standard out. And we've redirected where standard out goes. We've replaced the standard out file descriptor. As you correctly pointed out here, this should go to the file that we created. But because printf by under the hood, its implementation goes to standard out, and standard out is backed by the standard out file descriptor, it will also go to the file. Yeah.
If we wanted to write to the original standard out, we would have to store that file descriptor.
Exactly right, yeah. So if you wanted to retain the original one, you could use dupe to create a new one, create a new file descriptor for it so that it doesn't get closed, and then use dupe 2 to overwrite it. That's exactly right. So that's where you could use dupe. You could put a dupe standard out file no here to a new file descriptor, or sorry, we do it this way, to a new file descriptor, and then you'd have it saved. But yeah, that's a good question. But yeah, don't worry about that. Okay, so here's our redirect underscore standard out file. And what should we see? Oh yeah, sorry, go ahead.
Hold on. So if you run close on the original file descriptor, then the duplicate won't work anymore?
That's right. No, you can close the file descriptor. If you close it before you duplicate, you're out of luck. But yes, if you close it after, then you're fine. So what close does, it doesn't, kill the file or anything. It effectively removes it from the, you can think of it as removing it from this open file table. So that's exactly right. So if we call close on 3, 1 will still point to this file. It'll still be an open file. So close doesn't actually,
So
Yeah.
you have to close pretty much, if you get 3, you have to close all 3, right?
yeah, you would have to close all of them.
And if
That's
you
right.
don't, then you might run into this issue.
I mean, the only issue will be, you'll have a file open. You'll have extra memory usage in the kernel. That's what you'll have if you don't close files. Yeah. Yeah. Go ahead.
So if we keep track of this standard out file descriptor and the new file descriptor, and if you wanted to, let's say in this example that right now whatever you print in will go to the file.
Uh-huh.
If you wanted to print back to standard out, do you like fprint and
No, standard out is gone. It's already standard. It is standard out. So that's the key idea, is that standard out is not any particular file. There's nowhere that says standard out has to be the terminal. It's just because by default Bash will use whatever its standard out is. So if we write code in our process that overwrites or replaces that standard out file, it'll no longer be writable. Instead, whatever it writes to standard out, like printf, will go to that file. So like your colleague asked, if we want to save the original standard out, we could put it into another file descriptor with dupe. But no, we've replaced what standard out is. That's the whole key, is that standard out is not the terminal. Standard out is whatever file descriptor 1 is. And it's up to the process and the parent process to decide what that is. Yeah.
so you cannot recover the terminal out?
Yeah, no, it'd be gone. You could open the terminal. There is a file on disk, or not a file on disk, but there's a special device file that you could use to reopen the terminal. But you'd have to remember what it was. You'd have to record it somewhere. Or you could save the open file descriptor, like with dupe, and make a new file descriptor for that original standard out. But yes, once you replace it and you don't save it, it gets closed and it's gone. So if you didn't have any information about what it was, it'd be gone forever for that process. Yeah.
And if you wanted to convert two different files using two file descriptors, the only way to actually get that with printf would be using fprintf and switching.
Yeah, so fprintf will write to an arbitrary, not a file descriptor, it writes to a file. But it's the same thing with, you would just use, write and then the file descriptor, right? So that's what we learned with syscall. You'd just use that file descriptor. So printf under the hood is calling write eventually, and it's just writing to file descriptor 1 by default. That's why you can just write printf and you don't have to worry about where that goes. And it's not like printf goes to the terminal. Printf goes to standard out. And standard out is whatever file descriptor 1 is. So that's why Bash, you can have these additional commands to redirect things to files and do piping, because you can change where standard out goes without writing the program. You as the programmer can write agnostic to where standard out goes to and comes from, and then the system, the person operating the system, can decide after you write the program. That's the beauty of the Unix standard I/O abstraction. All right, other questions? Other questions on this? Okay, so let's go through this program one more time, and see what it does. So we write this message, write to original standard out, to the standard out file descriptor number. Then we open a new file. We replace the standard out file descriptor with that new files, that newly opened files descriptor. And then we write to standard out again. We don't write to that file descriptor, we write to standard out. So where will standard out be writing to now? It'll be writing to this file we opened, because we replaced what standard out is writing to. And same with printf. Because printf writes to standard out, it's going to write to whatever this file descriptor writes to. Because we've replaced that with this file, printf will now go to the file, not to the terminal. All right, so let's see that happening. So I run the program. The only thing we see on the terminal is write to original standard out, and that's because that's what the standard out was when bash invoked this program. After we overwrote or replaced standard out with this newly opened file, all standard out will be now written to that file. So if we open up that file, which is redirect standard out.out, we'll see both of these lines being written to that file. Questions on that? Yeah.
So you're saying that this whole file is basically what's happening as you call
The angle bracket. Yeah, that's what Bash is doing. Exactly right. Yeah. So Bash under the hood, when it creates the process, it's replacing what that process is standard out and standard in are. That's how those commands are. That's how that notation is implemented in Bash. And so this is actually, to give you a preview, this is what the next project is going to be. You're actually going to be writing a version of Bash that will support redirection. And so you'll actually process the commands and implement how redirection happens. So in the last couple of minutes, let me just, I'll go over this in more detail next time, but let me just show you how this gets, so to kind of combine this with process creation, to layer these syscalls on top of each other, what Bash does is it forks a new process, and then it does the redirection for that process before it calls exec. So the steps are create the new process, and so remember, that's still the Bash program running, and then redirect the output using dup2 and opening a file. And after that's done, it calls exec, which replaces the running program. So now that running program has whatever standard out, standard in, Bash gave to it. And the way Bash did redirection is before it called exec, after calling fork, so we have the new process and all the I/O. But before calling exec, it just changes what standard I/O standard out points to. So in code, that looks like this. So we open the new file, we call fork, and inside the child, we replace standard out with that file. And then in the exec version of this, after we change what standard out is pointing to with dup2, then we invoke the new running program with exec VE. Questions on this? So I'll go over this more next time since we're sort of out of time. But questions on this? So we're just going to combine process creation with fork and exec with this redirection in order to change where I/O goes for the process. All right, everyone. See you next week.